Okay, I still see a few people trickling in. I warmly welcome everyone to have a seat and would like to welcome all of you here who made it to Brussels and who made it to this meeting room, plus all the people online, to our final thematic session. Will be followed by a closing session afterwards, but this is the final thematic session. We will be talking about a cluster of projects addressing generation 3B. And as you can see here, the topic texts are summarized here. Both of them talk about generation 3B. The first one from 2019 is also putting a bit of emphasis on sensorization, preparation for manufacturing, whereas the second one is really going for high capacity and high energy cells. The second one falls under the BAT4EU partnership, which is, well, my main task together with Wouter to elaborate the work programs, the agenda, and the activities to be undertaken by the partnership. So first of all, 3D, I suppose as you're here, you know what it's about, but just to put everyone on the same basis, liquid electrolyte, high capacity or high voltage cathode, and anode composite of graphite and silicon. This, of course, is different from the solid-state batteries that all of us hear a lot about. A few years ago, that was really the big promise, but as we can all see, the introduction of solid-state batteries is taking a little bit more time than anticipated. There's also a few concerns with upscaling, potentially also the high-speed charging capacity. So I think it's fair to say that solid-state batteries will be important, but they won't be the silver bullet. And we need to look into other options as well. Generation 3B is a very promising candidate in the sense that it offers similar densities but is based on more traditional technologies. However, we have seen in the past from previous sessions in RTR, where we reviewed Generation 3B batteries projects, that it's very difficult to upscale these concepts and turn them into bigger cells because new phenomena arise. So I think it's a very interesting session today where we will learn about the different approaches and see how they are tackling the different issues and what promise is still left for Generation 3B batteries. Upscaling, by the way, is a concept that is becoming more and more central to the BAT4EU partnership. We are taking it more and more into account for the following work programs, also to make sure that the concepts and the manufacturing and the materials development all go hand in hand so that we come to a viable product at the end. So unfortunately, we have one speaker missing. You see on the right-hand side that 3 projects are announced. The middle one, SiGNE or SiGNE, however you want to pronounce it, unfortunately couldn't make it due to the strikes today, which means that we have a little bit more time, but it depends on you how you want to play it. You have more time for questions, or we can have a longer coffee break before the closing session. So up to you to see how you want to play it. Without further ado, let's move into the first project presentation. The project is Hydra. Hydra is working on cobalt-free sustainable batteries, but also investigating manufacturing and commercial implementation of the results. It will be presented by Dr. Simon Clark, who is a senior research scientist at SINTEF. Simon, the floor is yours. Let's give him a hand.
Great, thank you. Good afternoon, everyone. And thank you for the introduction. My name is Simon Clark, and today I'd like to tell you a little bit about our project Hydra, hybrid power energy electrodes for next-generation lithium-ion batteries. Our project was a Horizon 2020 project that began in September 2020 and recently completed in August of 2024. It's coordinated by Syntef, and we have a consortium of great partners that span academia and industry coming from all over Europe. Our project has four main objectives. The first is that we want to get rid of cobalt in the battery. As we know, cobalt's problematic for many reasons. It's not only a critical raw material, but can also have health and safety concerns. And when we think about what we need to do for the future, it's not just that we need to create 1 million of these cells, or even 1 billion of these cells. We need to create tens of billions, hundreds of billions. And if we want to do that, then we have to make sure that we meet objective 2, which is that we do this in an environmentally and ecologically sustainable way. But sustainability has two sides, not only the ecological side, but also the cost side. And we need to make sure that it's efficient and cost-effective to manufacture these batteries. So we aim to enhance manufacturing processes for the production of these new materials. Finally, this is a research project, so we aim to generate new knowledge. But of course, the ultimate goal is to support the industry in Europe. And to do that, we have Objective 4 to ensure fast commercial implementations of the results. So within this project, we're aiming to develop battery cells that are relevant for electric mobility, both for road transport and maritime transport. And we've established some KPIs to help us try to evaluate those things. So what did we do? Well, we created 3 generations of large format multi-layer pouch cells that range in capacity between 1 and 10 ampere hours. And this is important because when we're doing materials development, often things work very well on small scale, very well on coin cells, but don't necessarily scale up to industrially relevant pouch cells. So by doing that from the beginning, we tried to make sure that the developments and the materials that we create in Hydra are relevant for the industry. But I mentioned we're developing materials or researching materials. What are these materials? Well, we can see in the figure here, on the positive electrode side, we're using a material that consists of lithium, nickel, manganese, and oxygen, LNMO. Which is a high voltage material, obviously free of cobalt, and relies mostly on relatively abundant materials like manganese and oxygen. And where LNMO can operate at high voltages of like 4.8, 4.9 volts, compared with NMC, which operates at 4.2. On the other hand, we have the active material in the negative electrode, which is a mix of carbon in the form of graphite and silicon. And for the non-battery people in the audience, graphite is a very stable material, but not so high energy. On the other hand, silicon is extremely high energy, but not very stable. So by creating a kind of blend between these two things, we're able to get benefits from both and try to improve the overall performance. And we can see that by doing this, we've managed to reduce the critical raw material content in the battery by 33% compared to the 2020 CRM list and by 8% compared to the 2023 CRM list. And the reason for the difference is the addition of manganese, nickel, and copper on the critical raw materials list in 2023. So we've been doing work to improve the performance of the battery materials. We've been doing work to improve the sustainability of the battery materials. But as was mentioned, it's not just the battery itself, but also the production. How do we actually manufacture these things? And how do we manufacture these things on the giga scale? And one of the big challenges in battery manufacturing has to do with the very first step when you start to make an electrode. The first step is you take your active material powder and you mix it together with a solvent to create a kind of paint-like consistency that you can then cast onto your foil. And while materials like graphite are stable in water, so you can do water-based solutions, many of the cathode materials are not. They start to corrode. And so most manufacturing processes use organic NMP-based solvents in their manufacturing. And that starts to become a problem because NMP is very flammable. NMP is toxic, and flammable and toxic in battery factories means cost. So if we're able to reduce the reliance on NMP and instead switch to a water-based system, also for the cathode, then that starts to help us reduce cost and improve the sustainability of the overall process. And as we can see here, we were successful in doing that. The picture on the left shows a more traditional material, NMC, when cast with a water-based slurry, and we can see it's got these large cracks that come from the corrosion process, releasing gas and just kind of tearing the coating to pieces. And compared that with our slurry-engineered LNMO result, where we see nice, homogeneous, good coatings, indicating that with these slurry engineering methods that we developed in Hydra, this is indeed possible to do. And we see the benefits in the bottom left of the slide there of reducing the reliance on critical raw materials, improving the manufacturing process, with Hydra being able to achieve a cell cost between 59 and 75 euros per kilowatt hour, which is comparable with current NMC and LFP prices. So we've been able to improve the sustainability of the battery. We've been able to improve the cost. But how does it perform? You know, what's its performance metrics? And we can see that summarized in this slide, where on the left we see the specific energy and energy density of traditional chemistries like LFP in blue and NMC in red. And our Hydra technology lies kind of in between those two. So it's a cobalt-free material like LFP, but it's still able to achieve relatively high energy density and specific energy like NMC. So trying again to balance the benefits of these two methods. Secondly, we can show some electrochemical performance on the which side? The right side, where we see discharging rates at different C rates. And there we can see that even at very high discharging rates, even at 3C, which is discharging in 20 minutes, we're still able to achieve most of the capacity of the battery in this 1 ampere hour cell. And that's very difficult to do, even in automotive cells like the new 4680 design. They start to show really significant capacity losses even at 2C. And here at 3C, we're still able to get most of the capacity. So it's a very nice achievement, and we were able to do it by employing model-based design optimization methods. So within Hydra, we developed a tool which is free and available for the entire community, so everybody here, feel free to check it out later, called BEPA. And BEPA is a fast open source framework for doing physics-based battery design, simulation, and optimization. And there are two things that BEPA really excels at. The first is doing 3D simulations or P4D simulations on very complex cell geometries. So here we show an example of a 4680 cell, also prismatic cells like blade-style cells or multi-layer pouch cells. We can consider how the cell geometry affects performance. Secondly, it's very fast. We use a method called automatic differentiation, which allows us to solve the equations very quickly on the order of milliseconds, and that also opens up built-in optimization. So instead of having to simulate the entire parameter space, as would have been necessary previously, we can do 10 simulations, 20 simulations, and just walk up the gradient to achieve a design goal, in this case, optimizing the specific energy. Now, anybody who's done a PowerPoint presentation with videos knows my fear at this moment. I have an animation. We'll see if it works. Let's see. Hey, okay, great. And so we've been able to do this not only in a kind of way that's accessible to modelers and to programmers, but we want this to be accessible to everybody, including engineers. And so we've made this available as a web app interface, and you can check it out for yourself. It's live at app.batterymodel.com, APP. And there you can run simulations, check out your results, and as you can see in the time I've been talking, it's already done a simulation, so extremely fast solvers. Secondly, we've made all of the data from Hydra accessible to the community. I think especially now as we're starting to move into the age of artificial intelligence and machine learning, data is going to become one of the most important outcomes of research projects. And oftentimes this gets buried, or it exists but it's not really usable. And we've tried to address that challenge by creating, again, a web interface that allows people to explore data from the project and download it and process it in their own methods. So we can see some examples of that in the video. And currently there's data from more than 30 cells, some of which contain up to 12,000 cycles, and that contains both reference and maritime transport profiles. And yeah, again, freely available, free to download. So check it out, hydra.batterymodel.com. So as we come to the end and start to think about what has the impact of Hydra been, we can revisit our objectives. Did we develop cobalt-free hybrid electrode materials? Indeed we did. Reduced the critical raw material content by 33 to 8%, and demonstrated that you can indeed combine high voltage LNMO with high capacity silicon graphite in large format cells. Objective 2, did we improve the environmental impact and ecological sustainability? We did. We demonstrated that you can use water-based cathode processing and remove the presence of harmful and costly NMP from that process. Did we enhance manufacturing processes? We've showed that it's possible to do these kinds of things not only on coin cell, not only on single layer pouch cells, but also on relatively large scale multi-layer pouch cells that are relevant for industrial applications. And finally, did we ensure the fast commercial implementation of the results? We did. Our industrial partners Solvionic and Corvus Energy and Vianode have created new and improved products off this that are helping them to become more and more successful. And we can kind of summarize that again and just say that, yeah, our Hydra industry partners continue to gain influence. You may have seen in the news just 2 weeks ago, Vianode signed a $1 billion contract with General Motors in the United States to provide synthetic graphite. Corvus is supplying the tugboats for the Panama Canal. And Solvionic has released a new series of electrolytes called Solviolites for high voltage lithium-ion batteries. And I was reading in the news recently that this technology is starting to become more and more interesting also for other applications, not only transport. Apple and Samsung announced that they're starting to investigate silicon graphite composites for their phone batteries. But I think there's one element of impact, which I think is the most important thing. And I'll tell you a very short story just why I think that. There was an interview with Robin Zeng, who's the CEO of CATL, a few months ago, and it's on YouTube with a Norwegian investment bank. And he was asked, why is it you think that Europe has struggled in their battery industry while China has been so successful? And he ticked off, a few technical reasons, but he said, in the end, if you really want to improve your competitiveness, you have to invest in education. China has been investing in education of engineers and scientists and have trained a new generation. And if we want to have similar levels of success, and that's what we also need to do. And so I think that the people that came out of Hydra, all of the PhD students and all of the master's students and all of the postdocs and all of the researchers who will continue to drive battery innovation in Europe for the years to come will help us to continue to pay dividends. And I think that will be one of the real lasting impacts of the project. So with that, thank you very much for your time. Thank you very much for your attention. And I think we'll do questions at the end. So yeah, thank you very much.
Many thanks, Simon. So just a reminder, Hydra is the only project that you will hear this afternoon that is already finished. The other projects from the call 2021 under BAT4EU are still ongoing. So we're looking forward to hear how things are progressing. The first project from Bad4U that we will hear about is HighSpin. HighSpin is looking at, again, high voltage LNMO, silicon-graphite cells and modules for automotive and aeronautics. It's presented by Dr. Michele De Gennaro, who is the head of the Competence Center Unit Electric Vehicle Technologies at the Austrian Institute of Technology in Graz in Austria. And just to plug, this is also the host of the upcoming Battery Innovation Days in December. So looking forward to seeing you all there. Michele, please take it away.
Thank you. Thanks, Johan, for this kind introduction. AT is located in Vienna. That's very important, I know, not in Graz. Thanks to all of you for being here in this last session of the RTR, and also in quite complicated condition given the strike of today. It's with a true pleasure that today I present the HighSpin project, which is one of the projects that fall under the portfolio of projects that I'm managing at AET. So HighSpin stands for High Voltage Spinel LNMO Silicon-Graphite Cells and Modules for Automotive and Aeronautic Transport Application. And this project was funded under the Horizon Cluster 5 2021 Destination 20102 topic identifier. It was the first year of the Horizon Europe, and the third call that in the European program has funded projects for delivering Generation 3B high-capacity, high-voltage lithium technology. HighSpin has Hydra, also focus on the high voltage line, so on cobalt-free LNMO technology. The project started in September 2022, and it's expected to finish by the end of 26, so we are a little bit more than halfway. The consortium is composed by 17 partners, with Topsoe, Talga, and Arkema as a reference partner, as material provider and developer, respectively for the cathode material, for the anode material, and for the electrolyte material. We have many RTOs across full Europe involved, some as me and an end user, an aeronautic end user that is Pipistrel. The results that I'm going to present has to be considered as interim results of the project, so something that we can take a snapshot at month 24. So these are not the final results of the project. The objective of the project is to further develop the LNMO silicon carbon cell technology, extracting the maximum gravimetric energy density that is available from this specific chemistry. I speak about further developing because the project builds on a predecessor project that was funded under the Horizon 2020 LC-BAT program, which was called TRIBELIEVE. So we start from the TRIBELIEVE material baseline, and we do further develop the TRIBELIEVE material baseline across 2 subsequent iterations. We speak about iteration because we don't want to speak about generation, not to confuse with generation 3 and generation 4. So we assume TRIBELIEVE to be iteration 0 material. We have a first iteration of material that has been developed, and it's available today, which we call this iteration 1. And the project will finally deliver an iteration 2. But all the results that I'm going to present today refer to the iteration 1. The target gravimetric energy density that we have at cell level is 390 watt-hour a kilogram for more than 900 watt-hour a liter in terms of volumetric energy density, and the cyclability of 2000 deep cycles from 90% down to 10% of discharge. The application of the technology are, of course, targeting as primary market, the automotive market. We do see that Generation 3i, Generation 3b, they really find their application in the automotive market, their mass market application. But Generation 3b, specifically high voltage, high power application, is also particularly suitable to be the first generation that is applicable in the aeronautic market, up to a certain extent. We don't expect to see this generation on large civil passenger aircraft, but we do expect such type of cells to power future urban air mobility or unmanned aerial vehicle application. Together with this, together with the demonstration at the vehicle level, at module level, that is part of the project, we also expect to assess the technology against environmental KPIs and demonstrate the recyclability of the technology itself. So we target 90% recycling efficiency to be demonstrated at lab level with above 99% of material purity. So, as I said, I want to present a snapshot of the interim results of the project. So the results I'm going to present are focusing on the iteration 1, so these are not the final results of the project. And the first results that I want to present is the development of iteration 1 cathode material, just cathode material. So we started from the Tribelieve reference in this project, and we sourced the different types of LNMO from our material provider, Topsoe. Specifically investigating and analyzing the crystalline structure of the material. We have cycles, again, we have to be careful with the words, subcycles of material, and we have investigated a large number of subcycles of material, starting from single crystal to heavily polycrystalline material. We have developed a number of recipes, and we have defined one recipe that works better than others, which is capable of providing above 130 milliamp per hour per gram of cathode loading, which is quite satisfactory, and above 98% of Coulombic efficiency. This cathode then has been frozen, has been tested in half cell, and this cathode has been adopted for iteration 1 cells that we are producing. So you see on the slide some of the results, and this material is a multicrystalline material. The second result that I want to present today is the development of the high voltage electrolyte. We have seen from Tribelieve that the high voltage electrolyte was one of the major issues that we faced in extracting the maximum performance out of the cell. And in iteration 1, we decided to stay on an MP-based electrolyte, which is less environmentally friendly, also as Simon said, to move then in iteration 2 towards an aqueous process. So we start from a reference, an available, market-available reference, which is the Li PF6. And in iteration 0, we have already modified this reference for better performing and increasing the safety by adding some extra elements into the electrolyte formulation. We have further refined this recipe to achieve what you see on the slide, the iteration 1 reference electrolyte, which is the pink curve that can provide much better capacity and cyclability compared to the iteration 0 reference. The next result that I want to present, again, take this as an interim, but that's very, very interesting, is the finishing of the electrode. So we have seen that one of the major elements to extract more performance from the cell consists in the way the electrodes are synthesized and in the way the electrodes are structured. To do so, together with KIT, we investigated the possibility of laser structuring the electrode, which practically, simplifying a lot, it means basically carving a number of lanes, stripes, on the electrode materials. And we can imagine different patterns. We can imagine linear curves. We can imagine some rectangular shapes, or we can imagine some dots, basically. This laser structuring helps the diffusion of lithium-ion into the material, so helps the ability of extracting gravimetric performance from the electrode, but at the same time gives some physical room to compensate for the material deformation when the electrode is subject to high recharge or high discharge load. This is working particularly well, so we see this as a key technology to extract more performance from the electrode. And you can see in the blue bars in the slide how by laser structuring the electrode, we can significantly diminish the loss of performance at high C. We don't see big advantage when we compare laser structure electrode with no laser structure electrode. Up to 1C, we do see an advantage at 2C, but we really see that 3C and 5C is where this technology gives a lot of advantage. This is very, very interesting, and we are pretty much happy with these results. This is something that we can extend also at the anode. The results that you see here are at the cathode. And specifically, this is a technology that we can extend also to other chemistries. So this is something that is reusable across generation 3 and generation 4. Given the results that we got on the laser-structured LNMO cathode, we have also investigated different type of structuring. So focusing on the linear structuring, we have investigated the possibility of structuring the electrode with different distances, what we call here P factor. And we have investigated the unstructured reference against structured at 200 micrometers between the different linear carving, 400 micrometers, 600 micrometer, and we have found an optimum around 200 micrometer for this specific technology. And you can see how P200, what we call here in this slide, P200 provides us the best performance, and this best performance is particularly visible when we look at very high C rate, so 5C. Clearly, this is a technology that gives significant advantage, especially when we talk about high power application. And this is where I can connect to the what I said before, that we are investigating also solutions which are capable of serving different markets, like the aviation market, where we mostly have not only high energy, but we have to have high power application. The last result that I want to present today consists the coating itself. Within the consortium, we have two pilot lines, one operated by AT and one operated by SEA, but we have also a pre-industrial line, sometimes they call it pilot line or pre-industrial line, which is operated by SAFT. And we are investigating new way of producing and scaling up the material and the coating process. In this slide, you can see some of the results that we achieved with multi-layer coating. So basically applying the coating in a different way. So we have modified our machinery at the pilot line, and we have developed the methods to double coat the electrode. And in this way, we can achieve mostly double of the areal loading for the cathode. The process is not yet error-free. What you see on the slide in the picture is basically the electrode that has been coated, and you can see these small dots, these are small bubbles. So we're working in refining the process and upscaling the process. And this can also provide quite some bump in increasing the performance that we can extract from this technology. So these are the results that I wanted to present today. Again, these are to be taken as a snapshot of what HighSpin has delivered so far. Again, in the second half of the project, more or less, the nearly 2 years that we have ahead of us, 1.5 years, we are gonna further developing iteration 2 that will be an increment compared to iteration 1 results that you've seen here. We will keep iteration 2 at cell level, and in parallel, we are upscaling iteration 1 to have production of cells in batches of tens of cells, and we're gonna demonstrating the performance at the module level for an automotive module and from an aeronautic module. The automotive module will be a fairly standard one, the one that we have developed in IEEE. So, and it's an 8S module, while for the aeronautic one, we are developing a new type of module which fits with aeronautic requirements. So fire safety and thermal runaway, thermal runaway containment within the module. Concerning the impact that we can expect the technology beyond the market impact that is pretty much there, I think that I can recall almost the same thing that Simon has said. LNMO is a cobalt-free technology, and removing cobalt is one of the main advantages of this technology, being cobalt one of the most critical raw material. So the reduction in CRM demand is one of the drivers here, clearly. The picture that you see, the diagram that you see on the slide come from the results of IEEE, where we already did an LCA analysis of the technology. And you can see that basically if we compare at the same performance LMO against NMC 811, which is the best-in-class market-available technology, we have a reduction of cobalt to 0, but we also have a reduction of nickel and a reduction of lithium, which are other two critical raw materials. You save somewhere, you have to pay a toll somewhere else. That's a matter of life. LMO is more manganese demanding. But if we look at the environmental impact of this increase in manganese demand against the reduction that you have on the other material, you have quite a net advantage in applying this technology. Concerning the market entry, we expect, we have seen many technologies in the generation 3B and generation 4 to develop slower than expected or slower than wished. That's basically what Johan said. But we do see this technology slowly coming to the market point. So we do expect this technology to enter into the market by the end of this decade, maybe even a little bit before. And we also see many developments, one of which is the laser structuring technology that can be transferred to further future generations, so to be reused in generation 4. And concerning the market, we all know that our primary market is the automotive market. We do expect a demand of above 0.5 gigawatt-hour per year in the market. And we do expect certain demand rising up also from the air transport. Many discussions also undergoing into the Clean Aviation Joint Undertaking about the next generation hybrid electric regional aircraft. But I leave this for the question, maybe. So concerning dissemination and training, of course, we're going to publishing our results. We plan at least 13 papers during the full duration of the project. Some of them are already out. You can reach me out for if you're interested, and we're also planning to train 3 PhD students as part of the project, being the next generation scientists also at the very core of the value delivery of such a project. So that's all for today. Thank you for your attention.
Many thanks, Michele, for this very promising presentation. So now we're looking at the final thematic presentation of not only today, but the entire RTR conference. We will hear about the project NEXTCELL, which is introducing a new concept, the jellified cell. You'll hear all about it. It's a duo presentation by Dr. Danish Ifar, who is project manager at FEV France, and Mr. Sangvi, who is the technical coordinator from Avesta. Please, the floor is yours.
Good afternoon. Thank you for being here for the last presentation of the thematic presentation of the RTR 2025. Yeah, we are going to present NEXTCELL, which is high performance, high capacity, high voltage a battery cell also, but jellified. So Simon was presenting very well the chemical of and materials of battery cell, LNMO and silicon-carbon for the electrodes. Here we are using also the LNMO and silicon-carbon, but with carbon nanotube in the silicon side. So we are trying in NEXTCELL to jellify the whole cell concept. Components means like electrolytes with the electrodes. We are happy to work on the consortium with 17 partners. This is the project started in January 2023, and we have almost 2 years ahead to finish the project on December 2026. The amount of funding was 8 million euros. The coordination is FEV, and we have ABI as the technical coordination and SIE as the financial coordination of the project. The objectives of the project as presented here also with NEXTCELL, we are aiming to reduce the cost, also reduce the cost, also increase the safety and the sustainability. Saying cost, the methodology we are applying in NEXTCELL is jellification, but we are using the solventless manufacturing process, which help us to reduce also the cost and increase the safety on the project. The main challenge we're facing is mainly, as the other project presented, is on the development of the raw materials, especially that we are working on gellifying concepts. By gellifying, we are just mentioning that we are gellifying the whole components of the cells. The structure we have prepared on the project to advance on the aim to achieve the goals is first of all going through the requirements. So we have the requirements and specification. Then we went through the developments of the raw materials and developments of the cell. In NEXTCELL, we are aiming to larger scaling the project. So first we have this laboratory scale and small scale for 500 million per hour. Then larger scaling the cell for 5 amp per hour and 20 amp per hour on the cylindrical and pouch cell level, which is quite challenging also because on the manufacturing sides we need also to care the quality for large scaling, not only on the laboratory sides. We have the modeling, which will be presented later, the achievement that we have done for the modeling on the sites, and of course presenting recently new concept to the industry. We have the safety test and several tests going to be done in the next steps. So I will give the floor to Neil to presenting the achievement of the project.
Hello, a very good afternoon to everyone. So as it has been explained, we have a few scientific and engineering activities in the NEXTCELL project. And I want to explain some of the specific objectives that we have had. One of the main objectives at the end of the project is to have a high voltage format where LNMO is going to be a cathode and a silicon-carbon mix is going to be an anode. And in between the two, we will have a gel polymer electrolyte which is able to bear the high voltage offered by the LNMO. However, on the process side, what we are aiming to do is something very different from the state of the art. We are aiming for a gel concept where both of the electrodes and the electrolyte is going to be in a gel format. And for this, we aim to have we aim to not use any kind of a solvent, organic or inorganic. And on the course of the entire process, we will be using small pouch cells as well as the large pouch cells for the evaluation. One of the main points that we are aiming for is the validation of the main electrochemical KPIs at every cell level. Also, the aging protocols and the safety protocols that we are using are extremely realistic. They are based on the use cases which arise from the automotive use case as well as the stationary energy storage application. Also, in order to improve the quality of the modeling that is being done, we aim to use many advanced methods of characterization. For example, here we have a method which is accelerated rate based on infrared radiation to understand how the heat energy is going to spread inside the cell. Also, apart from the main electrochemical KPIs, we are having some other environmental KPIs as well. What we want to understand is that what is the cost impact as well as the environmental impact of the entire process, of the cell, of the raw materials, of the manufacturing process as well. There is also a substantial focus on recycling in the sense that we are going to have a flow sheet at the end of the 4 years, and we will be able to understand what is the extent of the recovery, what is the cost footprint and the energy footprint of the recycling process. And one of the partners is already having an online platform to record the economic and the environmental data, which we will be using here in NEXTCELL. So going to the modeling side, as it was explained earlier, we have a continuous back and forth exchange with the modeling teams in the partners, be it a development of the manufacturing process at the small pouch level, at the small cell level, also at the large cell level. When we look at the cell as an end product, we expect a certain requirement in terms of the aging, in terms of the safety, in terms of the performance of the cell. So in order to do this, what we understand is that when we look at the state of the art, the kind of models available do not illustrate the actual method of the silicon lithiation and delithiation. So this point is a substantial focus on the modeling. Also, when we look at LNMO, when we look at the state-of-the-art models, we do not have enough information on how exactly LNMO works. Also, the state-of-the-art electrodes are the wet-casted electrodes, but here we have a gel-based electrode. So the models have to be developed from a very basic level, which we are going to do and we have been doing from the past 2 years. I just want to give some overview of the achievements that we have had in the past 2 years. The validation of the anode material has already been done on the state-of-the-art electrode, and very soon the validation on a gel anode will also be completed. We have been continuously improving the surface area and the particle size of the anode material. Also, due to various reasons, because it is a gel-based electrode, there are some limitations on the electron transport. For this purpose, we study the incorporation of the CNT inside the electrode, and we look at the advantages. On the side of the cathode, we have validated the LNMO material on a conventional state-of-the-art electrode, and we will soon be doing the validation of the gel-based cathode as well. Here also, in order to improve electron transport, we focus on incorporating CNTs. When it comes to a GPE, it is a substantial exercise because what kind of the GPE we are aiming for is very different from the state-of-the-art electrolyte. And here also, we do not want any kind of a solvent in the manufacturing process, so this is extremely complex. And when it comes, if we go to the LCA side, what we have understood so far is that the material used in the anode and the cathode have a very large environmental impact as compared to electrolyte. This is in line with our expectation because on the cathode side, we have some important metals which have a very large energy footprint in terms of the mining, refining, and so on. Also on the silicon and the carbon side, there can be a substantial energy footprint. And so far what we understand is that the raw materials are 56% of the overall cell cost. Also, the recycling flow sheet has been defined. And when we focus on the GPE, it is very interesting because when we look at a gel, essentially you have a liquid, a solvent, and a salt, which are going to be a part of the manufacturing process and end up in the cell as the liquid part of the electrolyte. They have to have a flash point higher than 80 degrees. And also the boiling point has to be higher than 150 degrees, as in the solventless process, you can have a lot of heat which is being produced. The partners had begun from 11 combinations. They have reached to a small number of combinations, and very soon we will be fixing only one specific mixture. So this is a short overview of the modeling results that have been done. What you can see on the screen on the upper part is actually a mesh which has been made on a particle of the active material. On the right side, what we are able to see is the modeling which has been done for a thermal runaway. In order to validate the model, we will be doing some actual abuse testing in work package 5. Also, on the left side, you can see some of the modeling that has been done to model the actual electrode, as the electrode which we use here in NEXTCELL is very different from what happens in the industry in the cells that we use right now. And as with every European project, we focus a lot on the impact, on what is the effect of this European project on the industry and on all the other stakeholders. So to give a short overview, the activities that we are doing here, it is expected that if we are able to improve the KPIs, if we are able to have a better performing cell at the end of the day, for a given cell format here, it will encourage the other stakeholders to work on the cell formats, and it can be a more competitive landscape. The end user, at the end of the day, can have a better cell to use in their application. Also, apart from the technical side, what we expect is that we can have a cell which has a better energy footprint at the end of the day. Thank you.
Thank you all for these wonderful presentations and showcasing your projects. It's now my honor to lead the Q&A session for these projects. We have around a little bit less than 40 minutes left, so ample time for all of your questions. It heartens me to see that there's a good collaboration being going on with previous H2020 projects like 3Believe and Hydra, moving into the new projects like HighSpin and Intelligent, but at the same time, there's room for new concepts like a jellified cell as well. So there's a good mix of different things going on in this call. So thank you very much for that update. Has anybody have a question for one of the speakers? Please raise your hands, then we'll get a microphone to you as soon as possible. No. Yes.
Hello. Yeah. Thank you all for the presentation. Bozor Khamai from BEPA. Quick question from Michele on two sides. Maybe I missed the connection, but could you, if possible, elaborate a little bit on the laser structure design? So, is it the process and the manufacturing is the same, and then you apply the laser? And maybe I missed the link to the second innovation that you had in the manufacturing side, the multi-layer. What are those layers like? What's the difference in the material side? Thank you.
So you are correct. The laser structuring is a process on top of the electrode synthesis, and it's a process that we have explored as an innovation element compared to the previous project, the baseline project that we have 3Believe. And basically, you synthesize your electrode, and then you pass through this laser structuring. We have explored a number of different patterns, and we didn't do a full optimization because it might be really time-consuming. We don't have the full resources within the project, but we have explored different patterns, and we have explored different spacing, and we see that. As I showed into the result, that this seems to be the way to go in case we want to produce a cell which do have I would not say a negligible, but a significantly lower capacity penalty when operated at high C rate. And you start to see the benefits only when you go from 2C upwards. So up to 1C you don't see too much. So this is an extra step that you have to include into the cell production manufacturing. But that's pretty much interesting, and that's transferable. That's a very important part. Concerning the multi-layer, this consists in the application of several coating layers. So you can have a thicker and uniform layer of active material on the electrode, and you can achieve a higher areal loading. This is a way for increasing the gravimetric index of the cell. So this is expected to also give us a bump in terms of gravimetric energy index at cell level. And we have explored this as part of an upgrade that we're doing on our pilot line. So we have a different nozzle and a different, we have applied some modification to the coating machine to do that. And we see that we can achieve almost double of the areal loading, which will not translate in double of the capacity, but a good and non-negligible increase in the capacity at cell level.
Thank you. Just a follow-up. All this is to play with the high power and high energy game. So to make sure that
this is for the same material. So we are freezing the material and we are applying the material in a different way. And the idea is to go for high power, high energy. Yes.
Maybe a question from my side. A lot of the presentations focused on the cathode side of things. As the first thing, one of the first things that someone said is like, okay, we're mixing silicon, which is highly unstable and has its own problems with swelling. Is that something? What are the results first, Simon, from Hydra, and then maybe how to address those in the other covers, because it's quite an important part of the cell.
Yeah, thank you. It's a good question. Long story short, it's extremely difficult. But there's a variety of ways that you can address it. You know, it starts with your manufacturing techniques, just trying to, anytime you're blending two materials, trying to get a good dispersion of those two materials that you avoid conglomerates, especially in cases of silicon where, you know, the big problem is swelling and it just ripping itself apart. So you can get some improvements with good dispersion, good manufacturing properties. You can also start looking into binders, ways to try to counteract the swelling of silicon to hold it together. But it's a very difficult aspect, and I think probably the most challenging aspect of developing these kinds of batteries. It's something that we went through 3 generations in Hydra to develop. And it really took 3 generations to do it, but by the end, I think we were able to get pretty good performance out of it. But I'm sure everybody else has probably struggled with similar things. Do you have any insights?
Well, I think that silicon carbon anode is the pain in the neck that we all have, because in order to extract the maximum theoretical performance from the cathode material, we need an electrolyte working with it, and most importantly, an anode that does not function at the bottleneck. So as far as I have seen in the Hydra slides, you reach the 10% of carbon in the carbon anode, and at HighSpin side, we are almost at the same level. So we are flying in between 10 and 15%. We have done a number of trials at higher values, but at the moment, this gives us a lot of struggles in terms of instability. And I would say that the anode part is the one that at the moment is the limiting factor in the cell level. So at the cell level, so it's the element that is preventing us really to exploit the technology at its maximum potential.
Maybe Neil, from your side, what are your experiences so far?
Yeah, so one of the points which we've encountered so far is that when you have 2 materials in the anode, the way you mix and the way you blend and the way you coat is very, very important. And that is why in many of the consortia, we have a partner who specializes at the machine level, right? So that is why it is very important to have a machine level partner, because the state-of-the-art machinery, it may not be enough to handle these advanced materials and mixtures. Okay, yeah, so another endorsement for good machinery partners in your consortia and in Europe in general. Staying a little bit with the NEXTCELL project for now, it seems like, especially compared to the other 2 who sort of came rolling from already ongoing projects, you've chosen quite an ambitious lower tier well to start and make the same leap. What was the thinking behind that, and what makes you able to take a jump?
First, regarding the last question, I just add also that in NEXTCELL we are adding a carbon nanotube for the anode side, so it's a bit like probably more challenging also that we are going to the jellified also. So we have not still finished the project, so we will probably tell you in 2 years. Regarding the TRL, yes, we are in NEXTCELL, the aim is TRL 6, and as jellified cell is a recent technology, and starting from really basic like laboratory side, yeah, you're right. It's a quite ambitious project. We are doing with that, and we are doing our best. We have some promising results. Until now, we could achieve what it was like planned to achieve. And we're hoping to be able to present in 2 years the very promising results of the project on that.
Okay, great. Are there any other questions from the audience? Yes, there in the back.
Thank you, Michael Knassina. So I think Hydra was very clear in terms of KPIs. Thank you for this. I mean, it's the project that is finished now, so you reduce the cobalt in comparison to the different baselines, as well the energy density and cycles. Now it's somehow a state of the art. So I would like to ask the other two projects here. What are the energy densities you target? And you think I know that you are just in the middle, but what state of the art you actually aim to move forward? If you as well do the reduction of cobalt or the other chemicals, and maybe as well the discussion from the previous session. So I understand, at least it was mentioned, that you foresee these technologies being in the market by 2030, something like this. So it's still about 5 years ahead from now. Do you see as well any other tangible outcomes from your projects, in example like patents? Because you develop technologies, and I think it is something, a generic issue for all the projects in Horizon Europe, and I think the EGVIA chairman was saying that at the beginning. I mean, if you do the basic research, maybe you have the articles, then you have the demonstration, but what is visible when you are at about TRL 5, 6, 7? So this could be maybe the other area when you patent your solutions and you create the IPR for Europe. So if you could elaborate on this as well. Thank you.
Yeah, so just to speak about the KPI, so in the NEXTCELL project, one of the main KPIs we aim for is an energy density at the cell level in excess of 400 watt-hour per kg. And we still have 2 years, whether we meet it or not, but I would answer it in a way that the answer is much more complex in the sense that we may be able to meet the KPI at a small cell level, but we face an issue, which is for the upscaling of the electrodes. So it may happen that we meet the KPI at a small cell level, but we are not able to build the large cell because the upscaling of the electrode manufacturing and the electrolyte making is a bit complex. Would you add something for the patents?
Okay, so concerning KPIs, the reference that with whom we concluded the previous project, Tribelieve, was achieving 2/3 of the target that at that time was 300 plus watt-hour per kilogram. So we are at cell level around 220 watt-hour per kilogram with the previous generation, with what we call in HighSpin iteration 0. We have seen a bump up of 20%. So realistically, what we can get at the end of the project is to overcome the 300 mark. I don't think that we are going to reach the 390 watt-hour per kilogram, which is the theoretical maximum that we can achieve at cell level. But if we go to 300 plus, we are happy. At cell level, not at mini pouch cell level. So we are testing at pouch cell 8 times 10. And then we have a second cell format, which is larger for automotive application, which is 10 times 30. So this is something that we can pre-industrialize. So I think that this is something that we can achieve as part of the project, and such KPI would be already quite useful for end-user application in the automotive sector, and we are really at the lower margin for other type of application. Concerning the patent, of course, we have plenty of results which are patented and which the consortium partner are very jealous, especially at material level. So I mentioned that we have these 3 reference partners for the anode, cathode, and electrolyte, Topsoe, Talga, and Arkema. And we know that from their side there are patents existing and patent ongoing. And especially for the cathode material, Topso is quite well placed on the European market. So also there is a competitive edge.
Yeah, and just had a couple thoughts on KPIs and innovation, kind of along the same line. I started off my career as an engineer, so I tend to approach things from that perspective. And I think when it comes to KPIs, it's a good thing to keep in mind. Good enough for what? Of course, when we're doing development, we always strive. We want everything to be the best. Everything, high energy, the million cycles. Always striving for the best. But it's not always necessary. There's some applications where lower performing cells can have a home. I'll give you an example. I log being a battery scientist, I log all of the battery data from my laptop computer. And in less than 200 cycles, it's already at 60% of its nominal capacity, which is terrible cycling performance, but it's still in a product. And so my point is that I think when I think about the future of batteries and the future of lithium-ion batteries, we need to diversify applications. That not everything has to be best. Let's look at things that can also be for some less high-performance applications. And the second thought is with innovation. And I think this is something that we need to try to do better in Europe, because we do so much fantastic research. I think there's not much of a question that some of the best research in the world is done in Europe. But we generally struggle to convert that into businesses. And in Hydra, we've had some success with that. Solvionic, as I mentioned, launched a new electrolyte product line based in part on their developments. We've also done all of this development with BATMO and digitalization and battery analytics that we're evaluating for its exploitation potential. But it's a winding road to get there, and I think this is one area where we can improve in the future in Europe.
Yeah. I'll plant a flag on the innovation question, and quickly, before going back to the others, going back to Michele on the KPIs. Yeah, for some applications, maybe EVs, we don't have to push all the way for the KPIs. Your project is there's a plane in your logo, so you put the stakes a little bit higher maybe there. Given where you are in the project now and what you have seen, is there a credible pathway for Gen 3B as an aeronautics application, or do you think we're pushing it as far as we can, and the lessons we learn we can also maybe integrate in other generations, and that will be the one? Okay.
Definitely in the second one. Also in the aeronautic sector, we have a very diversified application. So we have urban air mobility that will come, will not come. There are different opinions but for sure there will be some unmanned aerial application for which Gen 3B will be good enough, absolutely. Gen 3B is more challenging safety-wise than Gen 4. So everything that we are learning on Gen B, we can easily transfer on Gen 4. So concerning the transferability of the results, which is an element that I have several times recalled into my presentation, that's quite an important part. The module that we will develop for aeronautics in Gen 3B will be absolutely valid in HighSpin for Generation 4. But when if we talk about putting actual people, paying passenger on an aircraft, we will most likely need solid state. And also the timeline is correct, because it's quite unlikely that any large-scale passenger aircraft will fly hybrid before 2035. And by the time, we should have hopefully made in Europe solid state generation.
Thank you. There's a question here in the front.
Hello, I'm Xavier Gillard. I'm working for the European Carbon and Graphite Association, and I have two questions. The first one, it's technical. I'm a political science guy. I don't have electrochemistry degree, yeah, I would like to be enlightened a bit on that point. It's about the recycling of silicon-graphite anodes. That is. Is it easy to separate the two materials in order to recycle them, graphite and silicon? or do they end up mixed in the graphite concentrates at hydrometallurgical recyclers output? And then when you heat it up, you end up with silica dust or something like that, which needs additional filters for the recyclers. So that's the first question. And then I wanted to pick up also on, that's the second question, on your remark, Simon, about industrialization. I've been in another conference where you had a consultant from McKinsey who was drawing up a slide about the various, type of anodes coming onto the market of chemistries. Some silicon-graphite anode are already coming up a relatively large scale on the market in the US or maybe in China also. Did you get your hands on those products in order to compare your own solution with those of the upcoming competitors somewhere in terms of performance?
Sure. Let's see. So on the first question on recycling, I'm not a recycling expert, so it's hard for me to make any kind of educated statement on it. But I can imagine that it would be very difficult to re-separate it out once it's blended in. But maybe somebody here is more of a recycling expert than I am. And then on the second question about comparing performance across different suppliers, it's a difficult question to answer. We do test materials from different suppliers from different places, and I think we've seen comparable performance across different things. It's hard to get into any level of detail, but so I'm sorry, that's probably not the answer that you're looking for, but I have to be careful what I say. But maybe somebody else has an idea.
Well, I can add something to the second question, because the first one is really, really specific. Concerning material that we find on other markets, at the moment, of course, we do have a look on this market. And at least at AT, we have done a number of testing on prototype cells coming from Asian suppliers, Chinese suppliers. And we see that concerning the anode, we are almost there. So they do have the same problems that we do have. They are more advanced than cathode and electrolyte in some cases, especially when it comes to gel electrolyte. But anode-wise, we are almost there. Concerning the first question, that's really, really, really specific. I know that there are dedicated projects which are just looking at that. So synthesis of graphite, synthetic graphite versus natural graphite, and recycling. So I would abstain to give any statement on that, because you have super experts just studying that specific part. So
so in the case of the NEXTCELL project, the experimental recycling activities have not yet begun because we are only halfway. But when you start from a gel-based system, it is not easy to recover the materials with a high level of purity, unlike a liquid electrolyte system where it is somewhat easier to recover them. Yeah.
Thank you, and maybe a good reminder that indeed we're now at the Road Transport Research Conference, and indeed the projects selected are towards the end-use applications, the dedicated projects on recycling, etc. You're more likely to find them at the Battery Innovation Days later in the year. So an invite to come there as well, Xavier, and discuss the recycling options there. Any other questions from the table? Johan, go ahead.
Yeah, if I may. Just a question for Michele. So this laser patterning process that you described sounds very interesting. I'm just wondering how compatible is it with mass production? Because I don't see it being used at multiple meter per second, for instance. Can you replace it by embossing, printing, something like that to get the patterns in?
Everything that we are doing in HighSpin has, of course, an eye on the scalability. So the same question can be easily answered for the second technology that I presented, which is the multi-layer coating. For that specific technology, we have a KPI of 5 meters per minute of coated electrolyte in a multi-layer frame. Concerning the laser structuring, which is also quite promising, at the moment this is done at a lab level, but it's done not at coin cell, but it's done at pouch cell. So it goes already in the direction of scalability. Of course, if you want to embed this into a high volume production, you have to go through the machining of that. But we think that this is possible. So this is already quite advanced.
Thank you. I'm looking for questions. Raise your hand if you want, then I can direct the microphone to you. I'm also triggered by your work on modeling, Simon, and data from the projects. You've put it all out there for everybody to see. How do you feel about the requirements for the European projects to do so? You've done it of your own volition, believing that it will benefit the community, but should we do more on this and to allow everybody to look at each other's data?
Good question. Yes.
How?
I think when we consider where the field is going, and not only batteries, but science in general, I mean, there's no question, I think, at this point that artificial intelligence and these kinds of machine learning methods are going to be the thing that determines the future. And how can we help the battery field come into that? I tend to look for inspiration in other fields that have done this really well and other fields that have benefited from it. And I think one clear model that we can try to follow is bioinformatics. I'm sure most people are aware of the Nobel Prize in Chemistry this year went to the AlphaFold people from Google DeepMind who made this machine learning model to predict protein structures. And when we think about why did they choose that problem, you know, they could have done anything. I think they chose it for two reasons. Number one, it's obviously a very high impact problem. But number two is the field of bioinformatics has had really good data management policies going all the way back to the 1970s. So today, when we have, you know, these extremely powerful machine learning agents that, you know, we need to feed with data to really get the benefit from, that's an obvious place to point at when we have so much data to feed it. If we then consider the equivalent circumstance in batteries, if we wanted to point it to a huge database of battery data, for example, to learn from, much more difficult. Doesn't really exist today. You can find different projects have posted things to Zenodo or their own databases, or in Big Map and Battery 2030. There have been some efforts to try to start coalescing this into a single place. But I think it has huge potential and huge benefits for the community if we're able to bring this together and to put it into a resource that we can point the power of AI and machine learning to use and learn from. And I think the main thing is just trying to now create the tools and create the support to allow people to do it. Because I think it's, you know, we're all super busy, all the engineers and scientists and everything. We've got a lot of time on, not a lot of time on our hands. So how do we make it easy for people to contribute to these kinds of things and easy for people to benefit and immediately see the benefit of doing it? So these are the kinds of questions that we're trying to answer. And yeah, as I mentioned, I think we can really look at successful fields like bioinformatics as inspiration for how we can move forward.
Thanks. Looking at I don't see any further hands. Just maybe for me, a last question is okay. You've just finished. The other projects are still ongoing. Maybe 2 years to go. But in the partnership, we always have to ask the question, what's next? So for Gen 3B, what are for you the key challenges that we need to get to this commercialization in 2030, starting maybe with Neil, and then we move this way. Sarah, go ahead.
For us, actually, as you mentioned also that we have like a quite ambitious goal on the NEXTCELL. We are facing two challenges. First, on the development of the laboratory, like jellified cell, and the second is to keep the same quality in the larger scaling the battery cell, so jellified. That's why like. We are struggling with these two challenges for the moment, and we are doing in parallel like larger scaling with like the development of phase, because we need to consider from the really early phases this larger scaling, as it is a part of like project, and we cannot just keep it at the end to go. That's why like we are struggling with these two challenges. We had some compromising results, and yeah, we are just trying to do best to see what's going.
Michele.
So,
you switch off. Yeah.
Material-wise, I think that we are at a turning point for Gen 3B, so we think that we are ready to step up to market. We see that some material providers still have some issues in the replicability of the processes. So sometimes provide material with the exact same quality might be a problem. So scalability of the production processes. And the other point, we are quite confident that today we can produce cell in an automatized way, but when it comes to insert new production steps like the laser structuring or like the multi-layer coating, machinery and scalability of the machinery is the other bottleneck at the moment. So that's I think very, very important, because one struggle that we have seen, it looks like a trivial thing, but it's true. I mean, when you want to produce a certain amount of cells with advanced chemistry, it's complicated sometimes even to find the tools on the market to buy to do that. So, and producing this tool and this machinery, it's something that it's quite important. And for this, we can look back at the 3Believe project that we have closed, where we had one of the 3 pillars of the project was dedicated to the conceptualization of the machinery that we need to produce for having a gigafactory. Implementing that plan would be definitely useful.
Okay, clear. Thank you. Simon.
Yeah. So I think, you know, when we look at the trying to bring improvements out of Hydra, I think one of the big takeaways, and one of the things that's starting to come, I think other people have mentioned it as well, is the difficulty of scale up and the really important part that plays. I think you mentioned it's a bit complex, which I think is the understatement of the year. It's extremely complex. And yet so important. And I think we've seen this play out over and over again, especially in the manufacturing field. You know, batteries seem on the surface to be relatively simple products. They're, you know, anode, cathode, and electrolyte. But especially when we look at how do you scale this up to, as I mentioned, you know, not only produce millions a year, not only produce billions a year, produce hundreds of billions a year. You know, do anything 100 billion times. Make 100 billion toothpicks. You know, it's hard to do, let alone something so complex and difficult. And so I think this is, you know, one of the aspects of Hydra that we've really tried to focus on is scaling up on pilot scale production, and will be one of like the key enablers or the key bottlenecks that determine the success of this going forward.
Thank you so much. Thank you all for presenting your results here today. Thank you, Johan, for the introduction. Thank you all for staying here. Hope you all get back home safe and on time. I wish you the best of luck also for the plenary session, which will start at 3:15 in the big auditorium next to it. And before that, we can still get a small refreshment in the area there. So thank you all.